This was an unexpected opportunity. I'm on the front end now of 4.5 hours of tutorials.
All right.
That's all right. So, but it isn't too tough because I teach. The hard part was actually narrowing things down, because I teach full courses on what I'm doing here in a tutorial. And so this morning I'm sorting through slides saying, how do I make sense out of this stuff in this much time? And so I'm hoping it's not jumping around too much and it's going to make sense. And but keep in mind there's a lot more to this than, as all of these things, right? As you could present in an hour and a half. All right, so yeah, this was really fun actually, because I work a lot in axiomatic design. You can tell I didn't waste time checking the capitalization on this slide, and it's neat to put it into surface metrology systems. Actually, looking mostly at surfaces. So, what is axiomatic design? Has anybody here used it before? All right, well, the neat thing about this is that it's based on the premise that there are two laws or rules that all good designs comply with. So we're going to spend a little bit of time looking at axiomatic design sort of as apart from surfaces, and then we're going to apply it to surfaces. And we'll be developing this. But I want to get this right up front, because actually a lot of the students here who use this think that axiomatic design is some of its components. The main thing, the heart of axiomatic design, is these two axioms. And so all good designs maximize the independence of the functional elements and minimize the information content. So we're going to be developing this. The issue, underlying issue here, is how do you tell a good design from a bad one? And if anybody's sort of supervised designs or design work, for example, I think this is particularly telling here. Because somebody comes to you with a design, they're passionate about their design. So designs are like babies; they look good to the people that made them. And so often, when you're in a design review, people are sort of defending their designs as if their genes were in them, right? And they want to get their ideas into the product, which is a good thing. But you need some objective criteria for doing this, and that's what the axioms will give you, and the stuff that goes with it. Because you can get into really long, non-productive discussions about this. So one of my former students, who's up at Hypertherm now, Mike Sapolsky, he actually got 3 degrees from here and was an All-American baseball player. But he said, yep, these design axioms are just the rules of the game. And he was at GE Corporate Research when he sort of came up with this. He says, it takes us from argument to analysis in design evaluation. So one of the things I was thinking is it's really kind of the grammar of design. Like I've gone in and I've taught this in factories or factory plants, engineers, and WPI, and given short courses on this, actually in Europe, and the United States, and Canada, and so lots of times, like when I don't know anything about batteries, and actually I worked on the space shuttle with this. I don't know anything about space travel. But this is the grammar of design. I worked on the Mars mission. This is the grammar. And so an English teacher knows something about grammar and can correct my engineering stuff, even though they don't know anything about my engineering. And so that's kind of what we have here. We developed a grammar for design. Is this working today? Yeah, oh, good. All right, so I'll try. So where does it come from? There we go. I got the wrong button. Oh, that's the laser I'm trying to do. Okay. So Nam Su. Anybody know Nam? He was at MIT for a long time. Yeah. And currently he's the president of KAIST, Korean Advanced Institute of Science and Technology. Actually, he's going to be returning sometime soon. We're actually putting on here the 7th International Conference on Axiomatic Design at the end of June. So if you'd like to learn more about this, we'll have a full day of tutorials and then 2 days of presentations, posters, and papers. And Nam will be one of our keynote speakers. Anyway, so he was at MIT and at NSF, and he has an honorary doctorate from WPI. We recognized his potential early on in his career. Actually, that was after I met him in about 1980 and learned about axiomatic design when it was still in the development when I was a graduate student. Anyway, so he developed that in the late 70s. And so, as I said, the premise is that there's sort of some self-consistent axioms that all good designs are based on. Just to quickly, he's got 3 books on this, and I'd recommend them all. They can be a little heavy going. Before I really could sort of get this, I read it 3 times. I usually don't have to do that with books. And when he came here to give a talk, I was all excited, and I've been teaching this course, and I was using this as a text. That was the first one. And then, so we get the room's all loaded up, and I got all the students there, and the president of the university, because he's got an honorary doctorate, and he goes, I really didn't intend this as a textbook. I go, Mom! Then why did you put questions at the end of the chapters? But, all right. Anyway, I think there's good stuff in all of this, and the neat thing is, here getting into the complexity, and you'll notice there's a fractal thing on the cover, and the next 2 tutorials I'm giving are about fractals. Naum also wrote, Tribophysics, and that was an earlier book about sort of tribology and physics. It's out of print, but it's an excellent book if you're working in something like bearings. Are you familiar with that one too?
Familiar with that one.
No. I should see if. Got to keep a lookout for cheap copies of these things. Sometimes on the web you can find them. All right, so historically we use what I call an algorithmic approach. In other words, you got a certain process, you go through step by step, you get the approvals, you chase down your boss, get them to sign off on something they haven't read for the umpteenth time, and then go to the next step, right? And then there's a lot of sort of trial and error, and it's kind of written into the procedure, so try, modify, right, and eventually you hope you converge. And how do you evaluate this stuff? Well, it's done by experience, right? So it's just like how did they build the cathedrals in the Middle Ages, and it was, I suppose, by having some fall down on some peasants and figuring out, oh yeah, we got to build this way. And so, whoops. How did I do that? There we go. There's no guarantee, though, that it's going to converge. And how do you know you're at the best solution? You've got no hypothesis anyway that says this is going to be the best solution. So in axiomatic design, we have the axioms, and then I'll be talking more about the structure and process for applying the axioms. Then we're going to take that into surface metrology, and the claim is that we get the best design solution for a set of functional requirements. Now this is a key concept here, and I know when I was working in industry, we often missed that completely. In other words, before you go someplace, figure out where it is you want to go. I mean, just don't jump in the car and start driving and then try to figure it out. But that's lots of times the way we do design. Right? All right, leave immediately. Where are we going? Nobody knows. All right. So the neat thing about this is that design becomes a scientific discipline. And a scientific discipline is one where we've got a compact set of rather simple rules that can be applied to a broad range of problems, like Newtonian mechanics. Right? So we can explain how apples fall off a tree and how the little lights move around the sky at night. And so there's a broad range of problems that can be solved when we understand Newton's stuff. All right, axiom 1. This is independence. And it can be used in the design process. Now, I apologize because, as I said, I pulled these slides in several places. So keep in mind here that not only the design itself, but the process of creating the design. Right? So everything gets designed, actually, and let me emphasize this point. Look around. What do we see here that hasn't been designed? How did you get here this morning? System that was designed. How do we put on the conference? All right, that's a whole system designed. Everything gets designed. So the system that we use for designing things can color everything. And not only that, we have to design the design process. right? Or we could design the design process and hold that to the same sort of criteria. So axiom 1, independent. So whatever we're designing, whether it's the design process of the product or the process to manufacture the product, we would like it to be adjustable, controllable, and we would like to avoid unintended consequences. Now, one of the simplest ways to think about axiom 1 is when I adjust one thing, I don't want something else to mess up. I would like independent control of, say, speed and direction in my car. I don't want to, sort of tie the accelerator to the steering wheel, and every time I turn right, I go faster or something, right? That would be an unintended consequence. Now you think, well, that's ridiculous. Who would do that? Think about your software that you use. Think about your computer. These are very complex systems, but and they're getting better. But particularly initially, Windows was a horribly coupled system, and there still is awful coupling, so that you screw up one thing and it brings everything else down. And with a little practice, you can start to recognize this. Actually, one of the things I tell the students is, all right, you may want to leave. You might not want to see the rest of this, because I'm going to tell you how to distinguish good designs from bad designs. And with a little practice, everywhere you go, you're going to see bad designs. And you're going to think, God, with a little bit of thought, this could have been better. I can see how this could have been better. So life is going to be more frustrating after this lecture. So maybe you'd rather go see how to do modal filtering and then avoid the frustration and knowing, God, that could have been better. So in the design process, what order do we design things in? What things can we do independently, and how do we adapt to changes in design? And there's a whole thing we can talk about in that, but I'll leave that for another day. There's three basic elements in axiomatic design. First of all, the axioms, and that's what we started with. And you can just, if you just thought about those and sort of took those home right now, you would improve all the designs you do. You can use them qualitatively, and I'll show you how they impact lots of different things. But you can also use it rigorously. And so just like, if we're going to use F equals MA rigorously, we can think, ooh, that's, a heavy thing. It's going to be hard to accelerate it. But if we wanted to say, well, like, exactly how much, power do I need to accelerate this, how fast, then I've got to have some system, and I've got to have like free body diagrams. I've got to be able to actually decompose the problem. And we'll recognize we've been doing decompositions and all kinds of things. And so we need some structure to the design. We need to put structure to the problem, and here it is. Now we still need a process for creating it. The algorithmic designs, I said, all they are is a process in some cases, but this has got the axioms, a hierarchical structure with two kinds of decompositions, and a process for creating that. So one of the ways of thinking about the domains, so we're going to start doing the decomposition, and first we're going to decompose into domains, and so the exercise that I give, if I had more time and we're doing like a 2-day thing on this, I would have you write it down. So I took this from a slide that I used in industry where we wrote stuff down. You could try it. So the trick here, though, is to get people thinking about, well, how could I describe these? And if you know what it is, you write down, oh, it's a camshaft. And then if you don't know, but then I say, okay, well, what else is it? What if, you didn't know it was a camshaft? How would you describe it? And so somebody might say, well, it seems to be like a cylinder with some things attached to it. And so you start describing the geometry. So the first thing was the function. Next you're describing the geometry. And then you might say, well, it looks like it's a ground piece of steel, and then you're describing the process. And so we want to be thinking about the surface and how the surface is going to react. And so then we take a look at this and think, so how do we describe the surface when we're trying to do surfaces? And we still can think about the function, the physical part. Geez, this looks like a series of ridges. It looks like it's ground, right? So what the function of this could be, I don't know, just to support the bearing on the camshaft or something. So it's a support surface, although this looks horrible for that. And I'm not sure where I got this. This is probably not that surface, but I took some license in doing this. All right, so we have the horizontal decomposition into domains. And it starts with the customer needs. So what adds value? And then the functional requirements, we'll be stressing this. What it does, where are you going? What do you want the design to do? And stating this clearly is key to good design. And then the design parameters, so physically what does it look like? These are things that go on a print. That's the physical description. Process variables, so how do you make it, all right? So that's like the grinding. And then there's also constraints, what things need to be avoided. So, and there's different kinds of constraints that you can have, and some of those will probably come up. So now as we take a look at this, we're going to be concentrating primarily on just functional to physical, although I'll get into a little bit of the process as well. But as I go from these engineering domains, functional, physical, and process, I have the same steps. Taking an element from the functional domain, how do I translate it to the physical and to the process domain? And that's kind of the challenge. So FRs, this is the functional domain. And so there's a few things you want to keep in mind, and I probably should have printed out cheat sheets for everybody. I'm sorry, but I actually finished the 3 talks I've got to give today 10 minutes ago. So you might want to just note, all right, so part of our shorthands, FRs, these are functional requirements. And these are the basic things. This is what you want the design to do. So they define success in design. In other words, if I've accomplished the FRs, I did what I set out to do, that's good. That's where I'm going. I got there. I'm happy. And if I don't like where I am, that was because I didn't have the right FR. Not a problem with my design process or the design method. I didn't know where I wanted to go. So provide the desired function. So design is about solving problems. And here's an interesting thing I was so brave to propose to the 5th International Conference on Axiomatic Design. I said, all problems can be stated as engineering design problems. And people should think, all right, so there's engineers, right? Not too much argument there. Okay, yeah, I can see that. Any problem could be stated as an engineering design problem. And I said, an axiomatic design is the best way to solve engineering design problems. That's the International Conference on Axiomatic Design, so yeah. Therefore, axiomatic design is the best way to solve all problems. So here we go. So design is about solving problems. So if there isn't a problem, you don't have to change anything. If there is, you got to change something. So FRs define what will be independently adjustable. What do I need to change or adjust? So adaptability to change, being able to change things is key to solving problems. So they have to be capable of providing change. So as we think about what the FRs should be, this is what we should be selecting. I'll say more about this because this is really key to making this work. Yeah?
Back on slide. I think your second sentence there doesn't meet these functional requirements.
My second sentence doesn't...
Yeah, no design will be something, then it's FRs.
No design will be, oh yeah.
Oh, what is the word?
Better.
Better. Oh.
Thank you. Good work, thanks. All right. No design will be better than its FR. I'll try to remember to correct that. And I'll make these slides available to anybody who wants them to. All right, so importance of adjustability. So be able to accommodate change. So change is everywhere, right? We're always dealing with change. If we were in medicine, we'd be dealing with folding money, right? Or banking, right? Folding. But we're engineers, so we're dealing with change. Okay. That was an engineering joke. How do you tell the extroverted engineer? They look at your shoes when they're talking to you. All right. So here's the problem. The universe is not in equilibrium, and I think if it gets there, there's some theory that would be the end of the universe. Something is always changing. Weather changes, people changes, so there's something you always got to get at. So why is calculus so important? Because it models change. All right, here's with respect to time. I could have just put dy dx. But that's sort of what Newton, and I don't know so much about Leibniz, but all right, something's changing, something's moving. And in Newton's time, they were just getting at being able to measure time. And so that was kind of a remarkable thing, that you could measure time reliably and then see how something changed with respect to time more precisely than people had done before. But so calculus is about change. So axiom 1's about adapting to change, and axiom 2 is about robustness with respect to change. So it's minimizing the information content or minimizing the complexity. And we'll get more on those later. If I elaborate too much, we'll run out of time before I run out of slides. So the FRs, as I said, define success in design, providing the desired function. I think this one is redundant. There we go. All right, let's move on to this. All right, so here's an example. And this is kind of fun because we look at sort of history of things. And so axiom 1 in breakthrough designs. So in other words, if these axioms really work, we ought to be able to look at any good design or advance in design and say, all right, so how do the axioms apply there? So here's one. I don't know how many of you are familiar with history, but in the North, we often call this the Monitor versus the Merrimack, because the Virginia, which is this ship here, was actually a Union ship called the Merrimack, which is a river in New Hampshire that was sunk and then raised by the South, and then refit as an ironclad with steam and lots of guns, and then this is the Monitor, which was made in New York and had its sea trials on the way down to engage the Virginia. So it's smaller, as you can see. It was slower, it was vastly outgunned, and it neutralized the bigger, faster, heavier, better armed Virginia. Axiom 1. First of all, steam decouples locomotion and wind, right? Both of those had that. So, and by the way, when the Virginia when the Virginia was launched and headed out into Hampton Roads, it just started sinking Union ships basically at will, because it was low, it was angled, and it was all iron and could go anywhere, sink anything. But the second decoupling was the swivel turret on the Monitor. And so there was a new FR, adjust direction of fire independently from the direction of the ship, because prior to that time, you wanted to shoot at something, you had to move the ship to aim the guns. Sort of like a World War I airplane or a World War II airplane. World War I, sometimes they had the guys out in the back, right? Anyway, so maximize the independence of the functional elements, right? So let's get a new functional element. So we can look at this in a matrix form. So here are the two FRs. One would be adjust direction of travel, the other is adjust direction of fire. So we have the rudder, essentially there's our physical thing that's going to accomplish these two FRs, and it does both of them. And so in this matrix representation, as we look at this, if there's an X, that means there's an influence. So adjust direction of travel, yep, the rudder's been good at doing that since, like the time of Columbus or something when they got the rudders working. And then adjust direction of fire, all right. That's what we call a coupled system, because I cannot independently adjust those two. Violates axiom 1. But I say, all right, these are the two FRs that I need to do. All right, I got the rudder for adjusting direction of travel. I've got the turret for adjusting the direction of fire. So there's the X where I want it. Okay, O means there's no influence. The turret doesn't change the direction of travel. There's an O there. There's an X there. Does this matrix look okay? So X means there's an influence. I'm going down to see, does this DP influence that FR? Put an O or an X there. How many people think it's a good matrix? How many people think it's a bad matrix? There's a mistake in it. And you're in the class, so I'm glad you got that. All right, what's wrong with it?
Well, the rudder will change the direction of the turret unless you...
Right. So anyway, so here's each FR requires a DP, so I can't keep these things independent if I've only got one DP. When we think about how we make surfaces and remove material, and so naturally coupled. So James is right. That should be an X there. So what this does is it takes us from, this is what we call a diagonal matrix, fully independent. Right? So I can adjust these things in any order. And actually what I need to do with the monitor is I need to get myself going in the right direction now the gun's not facing the right direction anymore, then I need to adjust my direction of fire. So this is a triangular matrix, and it gives us a certain order of adjustment. First I do this, then I do that. If I don't do that order of adjustment, at first I get the direction of fire and say, ooh, I got to go that way. Then I've got to iterate. In other words, that I've got to readjust the turret so I'm firing in the right direction. So I don't know what they were, how that worked out. And there were a lot of other problems with the monitor. If you read the history of this thing, it was able to shoot at itself because somebody had to be looking to see where it was going. And the captain ended up getting blinded, and the thing ends up, the turret leaks, and so it ends up sinking. But in terms of this part, all right. So this is an important thing. If I do it in the wrong order, I have to iterate. Now there are existing systems out there, and some that involve surfaces. And we're going to finish with an exercise trying to figure out what the right order is for selecting machining variables to get a surface the way you want it. In the existing systems, if you don't know what the matrix looks like and you start adjusting in the wrong order, you've got to iterate and see if you can get it to converge. You may be able to set up a matrix like this and solve the problem and go, oh, I know how to do it. That's what Namsu in his third book calls imaginary complexity. If I actually have a triangular matrix underneath things and I don't know it, and I start trying to adjust things in any order, then it seems like a complex system. Oh no, I've got to iterate, I adjust this, that gets out of adjustment. But if I put it into a matrix and then take a look where are the influences, the X's and O's, and then using laws of linear algebra, just rearrange the matrix, there's my order of adjustment, and the system is no longer complex. Right? It's like I found the combination to the lock. I can get in whenever I want. So what happened on this, on March 8th, actually, the Virginia comes in and starts sinking ships. On March 9th, the Monitor arrives, and it's kind of, there must be more behind this story. I read the little bit I could find on it. But the North, I think, knows they're making this. And the North bets on the Swedish guy, Ericsson, who's come up with this turret design. And they're hustling this down. And this seems like a gamble, huh? That I'm going to take this thing and take on this thing. And but it neutralizes it. And you can see in this depiction, see the Virginia's guns are firing this way and that way, not here. So he's about 45 degrees off the, I guess this would be the stern or something, right? That would be the bow because you got the flags in the front. Yeah, I guess so. Anyway, the smoke's kind of going that way. So all he has to do is just stay here, in this space off the bow or the stern where there's no guns pointing, and just keep pounding away at the iron on the Virginia until everybody inside has got a headache. And this so frustrated the captain of Virginia. And as a Southerner, this is an important insult. Northerner, we don't care, right? But in the South, he accused the captain of the Monitor not being a gentleman because he put a ship where he couldn't shoot at it. A gentleman would be a fair fight, right? And then you'd sink, go down with your ship like a gentleman. All right. So recognizing where change can increase value, new functions. This is part of innovation. And we talk a lot about innovation, but how do you actually do it? So if you can recognize, I got a coupled system, maybe all I have to do is just get in and figure out the matrix. Or maybe I think, there's a new FR. I can't adjust these things independently. If I could, this would be a much better system. So maximize the independence of the functional elements. So here's another, this is kind of a classic. This comes out of Nam's book. I've adopted some slides and enhanced it a little bit. But basically, when you want to go wash your hands in this style thing where you got a hot water valve and a cold water valve, is this a good design? How many people think it's a good design? All right, now we're being cautious, right? Okay. The first thing you have to understand is what does the customer want? Right, so if the customer, say, wants to wash their hands, all right, we would like water at a certain temperature and at a certain rate. So how does this thing work? Well, I've got, what can I adjust? I've got the cold water valve and the hot water valve. So if I look at the matrix, if I turn the cold water valve, yeah, that changes the temperature and the flow rate. And if I do the hot water valve, temperature and flow rate. And so it's an iterative process. So if you go into, you use a sink that you're not familiar with, you turn one on, you turn the other on, it looks about right, you put your hands, it's too hot, you turn up the cold, splashes all over you, too high flow rate, and eventually you adjust it. And so it's not serious, as long as people understand that your pants are soaked from the sink. But if you're making product, right, and you're wasting material while you're doing this and time and wearing out your tools trying to adjust stuff, so so you'd like to avoid this kind of system. So you have to iterate to get the solution. And so you need DPs. The best DP is going to address the FRs individually. So maximize the independence of the functional elements. All right, so some of you might remember the time when the United States could put men into space. We'll be able to do it again. We just have to go to Russia or China and buy a ticket. But we had some problems with this. We had 2 LOCs, losses of crew. It was designed supposedly for 1 LOC in 500 missions. And after we lost the Columbia, we were at about 1 in 50. So we're order of magnitude off in the undesirable LOC direction. So, is there some coupling here we could have avoided? Well, what were the functional requirements? Carry people into orbit, carry cargo into orbit. And what did we have? 1 launch vehicle. And for a long time, we knew how to dock in space, right? Was that Gemini or Apollo? Where we? I know before we went to the moon, that was a key thing. We had to be able to dock because we were going to take the lunar module and send it out. And then we had to get into, a re-entry vehicle, which was going to be hanging out. Anyway, so in orbit someplace. So so we knew we could dock. So why take them both up in the same launch vehicle? Why not use 2? And when we were looking at the new orbital space plane, and Nam called me one day, and it was the day before. I had said, I've got just too much stuff going on. I've got to say no to every project that comes my way now. Too often I'm like a kid in a candy shop, and even after I have a stomach ache, I still keep taking on projects that I probably shouldn't. Nam said, we're going to work on the crew survivability thing for the next orbital space plane. I go, no, I can't. I got too much stuff going on. He goes, engineering project of the decade, and had we made the orbital space plane, it might have been. So we spent a couple months working on crew survivability design. I thought about it for about 15 minutes and said, yeah, okay, I'll come with you to work on crew survivability in the orbital space plane. So the orbital space plane, the next generation of this, looked sort of like a Subaru station wagon with wings, and it just took the people and a little bit of stuff. And then you dock with something bigger in space, so you're not dealing with so much rocket fuel and it's such a large vehicle that has to re-enter. So anyway, maximize the independence. So they coupled the whole thing. All right, so after we get this independence, then the one that has the least information. Now, this is kind of funny when we're dealing with surfaces sometimes, and I'll try to address that, although I didn't take that on directly in this talk, but I'll mention it. We think, information's good. The more I know about something, the better I can deal with it. And that's information in a slightly different sense, and let's see if we can distinguish this.
Can I ask you a question?
Yeah, please.
So, with the space shuttle, right? Probably one of the reasons that they had it the way it was because it was impressive, right?
Yeah.
That's the way to get it funded. So is getting the project, paid for or supported? Is that a functional requirement? What do you call it?
Cost is a constraint. So a constraint might be getting it by Congress.
Okay.
right? So there might have been some other ways to get it by Congress that didn't require you to make it look so impressive in that sense, right? But I think they could have gotten it by Congress. I don't know. Who knows with Congress, right?
So functional requirements are independent of like human intervention, right? So any human dimension of the problem, right? It's getting the job done, whether it looks nice or whether it.
Well, aesthetics can be a functional requirement. Okay. No, if I'm making products, and I mean that's a good point. If it's got to appeal to Congress, I need something there to make it appeal to Congress. Now, more boondoggles, free trips to Florida, right, or something. Who knows? Here's free tickets to the nightclub. I don't know. Find out a DP, that will address this FR, get enough votes in Congress that doesn't require you to change your basic design that was good, right? That would have been. But in the case, you're dealing with papers, and there's a lot of aesthetic stuff there, right? So sometimes we'd like to be phooey to aesthetic engineers. Let's make sure it just gets the job done. We don't have to worry about this. Hell with aesthetics, right? And that's sort of characteristic of engineers. But you go to sell something, that's a real requirement. So I need to know, all right, so what makes this look good to, New Englanders or something that looks a little salty and not too well, sort of pressed or something, right? But would that look good in Wichita? I don't know, right? So, you got to know. So if it's to sell to a certain group or to make it look appealing to a certain group, you can identify the characteristics that'll make it look good to that group and include those. But there may be more than one way to get Congress to vote for it besides having it big, right? Just make sure the money for, they get some money in their district, right? Have lots of components that get made all over the place, which is, all right, anyway. All right, so maximize the probability of success. That's what the information content is about. And so we want to minimize the possibility of errors, minimize the impact of wear, temperature, other variables. It's a robust design. And sometimes we can actually use surfaces to increase the surface roughness to increase the robustness of the design. And so when we're trying to fit parts together to make a seal, one of the theories that we're working on is that we would like a very peaky kind of surface. So when we move these together, we can scrunch the peaks and help to make a seal that way. Maintain the independence of the functions. If we think about single FR design, sometimes we can get to a branch or we can isolate it, and then it's all about kind of axiom 2. Let's look at a quick axiom 2 thing here that I use in teaching axiomatic design in general. And I'm sorry I didn't have time to develop maybe a better one on surfaces, but this is maybe good in simplicity. So here we want to clamp these two elements together, and we've got a sort of clamp thing here where this element is a spring, and so if I open it, I've got the shorter diameter, right, on the shorter dimension, and when I close it, I have this longer development thing, so it stretches the spring, and so I've got a clamping force, F, is equal to Kx, right? So my dP is sort of the clamp displacement, major versus the minor axis, and my FR is the force. So the question is, which is better? Do I want a stiff spring, a big K, or a little k? So how many people think I want a stiff spring, big K? How many people think I want a soft spring, a little k? How many people don't want to commit? You can just watch this guy. He's in my class, right? So he's been through this.
I'll go soft.
You go soft, all right. So as it turns out, before I looked at this, would consistently have picked the wrong one, thinking stiff. Oh, I want that to be really solid. I want to be able to put a big force in that. In fact, on these kinds of systems, I've got a force plus or minus something. An example of this would be like a hubcap. I don't want it to fall off when I hit a bump, but I still, my weakest driver that's going to be changing a flat tire has to be able to get it off. So I've got a maximum force based on removability, and I've got a minimum force based on hitting bumps so it doesn't fall off and I lose it. So there's a whole bunch of systems like this where we got a sort of maximum minimum force kind of thing. And then, so the stiff spring, if we take a look, so here's the X, right? So here's how much displacement am I going to have on the spring? So if I have a stiff spring, I need very little displacement. And often you go with that design because you don't have much space, right? So you kind of say, how much space do I have to do this? But if we've got lots of space, I like to go with a softer spring because you see, this is a small tolerance and this is a big tolerance. Right? So I'm much better off with a big tolerance. So how many people here do DFSS? Do you? So when I've taught this before, so it's designed for Six Sigma, designed for big tolerances. And when I've taught this before, I say, geez, when you did DFSS, did they tell you how to do the design? They always say, designed with big tolerances. So yeah, in the print, I could just increase all the tolerances. That was pretty easy. But how do I know it was going to work after I increase the tolerances? And so here's a system to do that because I keep the force in the range where I want it to be, despite temperature change, wear, manufacturing variability. So softer spring. This can be a metaphor for lots of things. I mean, you could think about this in economic systems and all kinds of other things. Nam helped go back and redesign the Korean economy. And he's helped the World Bank with design, so it doesn't apply just to sort of mechanical systems by any means. All right, so that's kind of what we're talking about. So there's lots of applications for this information content. So when I put it in terms of information, I didn't give you the formula. It's like entropy. So the information is equal to the log of 1 over the probability of success. But we don't really have time to get into a lot of the quantification of this. All right. So in order to try to impress people on the universality of this, any problem can be solved. I can design anything. All right. So here's designing a vacation. All right. So FR, get some relaxation, get some romance. Could be 2 goals for vacation, right? 2 FRs. So what would be the DPs that would go along with this? So relaxation, ethanol, and romance, say dancing. Okay. So what's this look like? Well, so the ethanol is going to influence the relaxation and possibly the romance because it may not enhance the dancing at some point, right? And so the question is, can I compensate for the bad effects of the alcohol by more dancing? And people with experience would probably realize, no, you probably can't after too much alcohol. Actually, you can't do that. So not only is this somewhat less desirable than a diagonal matrix, in fact, we may not be able to fix the bad effects of the first DP with the second DP, because that's kind of what we're trying to do. All right, let's get relaxed, and if we needed a lot of relaxation, we may be way too relaxed to be able to perform on the dance floor. So what we do in this case is we look for another DP1. So instead of alcohol, if we used yoga, all right, then we would be better off, and the matrix would be a diagonal matrix and fully independent. So that would be a much better solution. So not surprisingly, ethanol is not a good design solution, right? We said this could solve any problem. So here we go, proof that alcohol is not a good solution to problems. And then yoga might be better. All right. So we want to maximize the independence. So here we clearly haven't done it, and there we have. All right, so what we're trying to do is satisfy the FRs, and a couple design has got less chance because adjustability is difficult or impossible. And after removing the coupling, the probability of success can then be applied to axiom 2. All right. There is so much low-hanging fruit. There are so many coupled designs around that if you just remember that first one, you're going to be in good shape. So avoid unwanted coupling. So what distinguishes a scientific discipline? This was made for a day-long tutorial when people could actually kind of take a quiz. Well, let's see if you've been paying attention. So what makes something a scientific discipline? Oh, this is disappointing. All right, a few self-consistent laws. All right. What are the elements of the functional domain? Functional requirements. What a design needs to do. What are the elements of the physical domain?
DPs.
DPs, very good. All right. What is axiom 1?
Independence.
Very good. Maximize the independence. Why is axiom 1 important?
Better when things are independent.
All right, yep. Adapting to change. Very good, Laura. Axiom 2, in terms of probability of success. Maximize the probability of success. All right, so it's lower stiffness, lower modulus.
So your tolerance.
Right. Very good. All right. So let's take a look at a problem now in surfaces.
Can I ask you a question before you go?
Yeah, sure.
So how does biological design or evolutionary design fit into this?
That was such an intriguing question for Nam that when he started sort of getting into that, he took Bio 1 at MIT to try to figure it out. Yeah, so one of the things we see in sort of people-based design, right, is we see some evolution and things get towards, decoupled designs over time. And so the question is, does evolution go that way? Or did the intelligent designer, depending upon what you think about how the universe got the way it is, did the intelligent designer know the axioms? Or did the intelligent designer think the best way to adapt would be evolution, and therefore evolution is intelligent design? But when I've tried that on my friends who believe in intelligent design, they don't buy that, so I don't know. I said, if it was up to me, if I were the intelligent designer, I would say, evolution. We got it. It's going to adapt to change. Yeah, so it depends. What are the FRs? Yeah. So as Kurt Vonnegut noted in one of his books, I can't remember, he's these little things, a little thing where somebody used to talk to God. And he says, God, why are we here? And God says, reproduction. I really don't care about anything else. and there's some logic to that, right? Why are we here? Because we were able to reproduce. If your parents didn't have any children, you won't either. So it's survivability, and it's the FR. Adaptability is part of that.
The reason I'm asking that question is because it seems like, in evolution, right, one of the approach is create a lot of stuff, all the different possibilities,
right,
and then prune.
Yeah.
Right.
Actually, when I talk more about innovation, so what's the best way to have a good idea? Have lots of ideas and prune. And how do you prune? Test them against the axioms. So, the biomimicry, did biology get the right answer? There's a lot of that. There's a lot of that in surfaces, and that's the lecture I'm replacing, unfortunately, or 2 lectures I'm replacing. We're going to look at that, and I think that's fascinating stuff. But one of the things we got to remember, how long did man try to fly by imitating birds? And how well did that work? So, so we have some pretty good systems that we don't see in nature, like we were talking about yesterday, ball bearings. Anyway. All right, so rotating lip seals. These are where I got a shaft and I've got sort of oil on one side and nothing on the other, right? Air on the other. And a little bit of reflection, we'll figure out how important these things are, because we tend to convert chemical energy to mechanical energy in oil-rich environments. And then we've got to get the power out of that oil-rich environment, like to the wheels of the car. And we don't want to keep splashing oil on the thing because we would need lots of oil, so we need to contain the oil inside the power conversion unit and get the power out. And so that demands that there's a little seal here that keeps the oil on one side, right, and the air on the other. And if that fails, it's a problem because it's like on the main sort of the powertrain. And so you think about what you have to take apart to replace that seal, and it's kind of like the whole car. Right? This is right in the middle of the whole thing and the most important part. The paint job gets the car out of the showroom. The powertrain gets you to work in the morning. So if we look at this in some detail, so we've got some sort of bore here, here's the oil, there's the shaft that's turning around, and we need a little seal right there, and we need to make sure somehow, and we might imagine there's a little meniscus, or there's actually rubbing here or something. We need some way that we don't wear this thing out too fast. And so right here is a critical surface, and it's on the shaft. Now, it's interesting that the RMA, the Rubber Manufacturers Association, came out with a triple double-sided tolerance for the shaft. All right, so, but with a little reflection, I think we can imagine why they did that, all right? Because the seals are rubber, the seal is wearing out, and you blame the seal, right? God, this stupid seal wore out again. And so the people there go, how come our seals are wearing out? And the thing is, it's the shaft. So we need to get the counterface right. So this is essentially a recipe, as we'll see, for a plateau-honed surface, at least in some sense. So ISO has actually got just 2 double-sided tolerances, but I was looking for something that was more difficult to design, so I'm going with the RMA spec with 3. It gives me more to talk about. All right, so what's the problem here? Well, if we know something about surfaces, and I'll elaborate on this, these are not independent. So if my FR is, to process this, to grind this thing, is provide an RA of this, provide an RZ of this, provide an RPM of that, they're not independent. And that can lead to some problems in processing. So you guys do seals, right? You have double-sided tolerances?
Not typically.
No?
Sometimes
Sometimes,
depending
yeah.
on the surface.
Yeah. All right, so they're not independent. So this violates axioms 1 and 2. And there's iteration required, and we'll take a look at that. Just to emphasize this now, so RPM is the peak height, this is above the mean line, and RZ is the peak to valley. So the mean line sort of splits the profile. So if we had a roughly ground surface, we might be looking at something like that schematically. And so RVM is the valley depth. And so if these two are about equal, peak height, valley depth, then RPM to RZ would be about 0.5, right? No heavy math there. So if you remove the peaks, as in honing, and this is getting down now to a nice bearing surface, the point being I've got places here where I can store lubricant and where debris can end up, and then I've got this to support the load. And when I push on this, a little oil comes out to lubricate the interface, so that's a nice design. And so when I do that, the RPM-RZ ratio goes from about 0.5 to something like 0.25, and that's the plateau honed surface, and you call it a full profile because if I put lines across here, I'm mostly in the surface when I'm close to the top of this. I've got a lot of sort of material to support a load. Now, here's the point. I can't change RA independently from RPM and RZ. So if I put more valleys in, that increases the RA. And it also changes the mean line. And now, since the mean line changed, the RZ could be the same, but the RPM will increase. So that's an example of how this is a coupled system. So I can't independently change one from the other. And we can take a look at some of this. So let's think about the RPM, RZ space. So how are these things likely to be coupled? Well, one of the things is, if this is the peak height, I can't have a greater peak height than I have peak to valley. So I could draw a line across the middle of this and say I don't have to worry about the top part because that's mathematically impossible. So actually it isn't at all likely right on the line. It becomes increasingly likely as I get a little ways away. Now, when I go to process something, there's going to be some inherent kind of RPM-RZ ratio. And so if I take a look at this, I might say, oh, this is pretty consistent. Now, when you're dealing with like a manufacturing process and grinding things, you can say, oh, I can change, the RPM and RZ, they change together and they tend to work along this line. If you're looking at bones that have been sitting on the bottom of the ocean for a while or something, there may be an inherent RPM-RZ ratio that would use to characterize that might be different and it might be more useful than either one by themselves. But as we're tolerancing things, we go, all right, so there's the top end of that tolerance, there's the bottom end of that tolerance. And when I spec it the way I did, it is a rectangular tolerance. So anything in that space would be good. So both of those are going to be sort of indicate moderately full profiles. So good bearing area, good lubricant storage, get the stuff out of the way. But the question is, in that rectangular tolerance, what about the other corners of that rectangular tolerance? Those might not be so good. So how are those going to function? I don't think anybody knows, because the variety of surfaces that you tend to prepare to test are all on sort of the same machine. If that's the machine you're going to use and you're doing this stuff anyway, okay, who cares? When you source it, though, to somebody else, and somebody else that doesn't speak a language even approximating English, who knows what you're going to get, right? I'm for making things close to the point of consumption so that you... so anyway, this would not be good. But those would both be within that tolerance. So Nowicki, I think I'm pronouncing this the way it's supposed to be, but probably not. In 1985 already came out with this multi-parameter representation of surface roughness. And it's a paper worth reading still. And keep in mind this was written when Poland was still behind the Iron Curtain. So one of the questions he's asking, which I think is important in sort of forensic kind of work, anthropology things, is if I'm going to use just a limited number of parameters to describe things, which I might like to do, right? Why have more? Which ones should I choose? And I should choose the ones that are the most independent, because I'll know more about the surface. And interestingly enough, and you have to be careful of falling into this trap when you're thinking about axiomatic design. I've got more information. Oh wait, no, I don't want, more information is bad. And that's in the wrong sense of information. Knowing more about the surface is good, because the chance, all right, the probability of success, the probability that I actually spec the right surface goes up when I describe it better. And so in one sense, I think I've got more information about the surface, but that's using information with a different definition. I know more about the surface, knowledge is good, and my chance of success, my chance in describing the right surface goes up if I have two parameters that are decoupled. So what Nowicki finds is that the peak spacing, which is a horizontal parameter, and I don't have his results up here, is very independent from the height parameters, and the height parameters are highly correlated. And I just made this up, but essentially what you're doing is you're looking for a plot, say, of RA and RQ. And these are, RMS height and arithmetic mean height, and they're highly correlated. They're not exactly the same. And so you could plot these things, and you get a correlation coefficient. So you make a correlation matrix like this, and you can take a look and say, well, which parameters are going to be the most useful? And so, the parameters that are the least correlated, because you can actually write an equation, as I did here in this paper, where we're looking at a specific process. And this is EDM of ceramics, so it's kind of a exotic process. But in this particular thing, it's going to be highly specific to your to your situation. So if you're looking at, and it could be different manufacturing processes or different things that have happened to, stone tools or some, use wear, whatever, degradation. These matrices will look different. The relationships between these will be slightly different, but the height parameters are always going to be highly correlated. And here we can see these are two parameters that come from the fractal analysis stuff that I'll be talking about later. And we can see these are not at all correlated, right? 0 is the least correlated you can get, right? And this is basically, there's no correlation there. So when they're correlated, it means, and these are linearly correlated, we just write an equation. And that means, so this is R we put in this matrix. You can tell it's R, not R squared, because I get negatives, right? And this means that 82% of the variance in RZ can be explained by the variance in RA. And so these are also highly correlated, and 84% of the variance there. Okay.
Chris?
Yeah.
So, I mean, maybe this is happening for obvious, but what it seems like is going on, you have your measurements, right? And then you have your dimensions or your information, right? So why do you need to be stuck to your measurements? Why can't you just do like a PCA or something and come up with some other dimension, which is more...
There you go. Yeah, you could, right. But why are we stuck with that? Because we need to be able to communicate about this. Everybody knows what RA is. And so if you're working in isolation, yeah, you can do whatever you want. But if you're making components for somebody else, then you need to educate them. Oh, we're going to do PCA, we're going to do this, right? And so in the whole supply chain, right, you've got somebody who's making the machine to make the part that goes to the person that maybe assembles a subcomponent that goes to, right? And so it's standards work. And so this is one of the things, that takes time. Right now, 90% of the industry in the world works on RA, even though it doesn't make sense. Maybe it's not the best thing to use. And in airframe manufacture, for example, they use RA. And what they're trying to do is prevent little sharp V's that'll lead to fatigue cracks. But and RA isn't going to be the best because a sharp V is the same as a round bump, right? And the round bump isn't dangerous at all. And they have parts that they keep in machine tools. Well, this was at the Kent machine shops that they've closed, that Boeing closed, but that was for their military aircraft. But they have components that are there where the tool's just going back over and removing little ridge marks, which probably wouldn't be dangerous for fatigue. And they spend days, sometimes weeks in the machine tool that they were charging over $100 an hour for, in their internal thing. And so that was something, we'll source it, right? So they got rid of their machine shop. But yeah, so that's the problem. So the wrong parameter can cost you a bunch of money, but are you going to go back and try to go through all the mil specs or the FAA and say, all right, now we're going to change the way we're characterizing the airframes, and you go, they're not falling out of the sky now. So we might be able to change something. But here's on the cautionary side is, so what if some country is newly developing their aircraft manufacturing capability and they decide to use something else? So we get beat. So here's a systematic iteration thing. I'm not going to go through this in a lot of detail, but so if you're trying to meet these coupled tolerances, let me quickly show you something we came up with. And so the idea is you do sort of two trials. So you get your incoming parts, and you say, all right, let's try feed, speed, whatever, some process variable, and try two different values of it. And then let's see where the RA tolerance fits on this. So I have an RA axis, and now I've got the process variable axis, and there's the RA. And now I'm going to put an RZ axis on this, but I've got to scale it specially so that it corresponds now to the RA axis. And then I put the RZ tolerance on it. And then I do the RP that's also fitted with the RA. So that the way that happens is that these 2 points are plotted there for RA, and in the RZ axis they have the same location on the plot. So that means I had to stretch or shrink the RA axis, which is going to be linear stuff, right? It's going to be, micro inches or millimeter, micrometers or something. So I had to stretch this or shrink it so that these points line up with the RZ axis and the RA axis. So these are three separate axes, and the numbers are either closer together or further apart on those, depending on what I have to do to plot those 3 points. And then I put the tolerances on there, and so this is the cleverest way we could come up with dealing with this coupled system. And so now we can see, this is in the RA, but it's not in the RZ and the RP. And so then I say, all right, first approximation, let's assume it's going to be a straight line through everything. And then let's see where our overlap, so there's the tolerance overlap for this system. So here is the process variable value that we're going to use for trial 3. And then we can see where that ends up, and it might not be quite linear, so then you do it, you keep doing it. And trial 3 might not be a point because I got to plot all 3 of these, so it may be more like a smudge there. Anyway, so this is its iteration, and it's some sort of directed iteration, which is based on old-style artillery stuff, where bracket your solution. Anyway, so these are not independent, and so this is problematic. And
so what are your favorite axes? Is it this?
What are my favorite axes?
RPM, RZ ratio? Yeah, what have you found to be the most useful axis system for displaying your structures?
It depends on the problem that you're trying to solve. And so the simple thing on this is
do the matrix.
Try them all. Try them all, let the computer sort it out. Right.
And then do you fractal, like have some of your fractal analysis coupled with the RAs?
Yeah, we test that. Yeah, we've tested that. I don't know if we published anything on that, but so not many people are speccing things with the fractal stuff, but they might be better off they did, and I sort of wind up, I think, with an example of that. So suppose we looked at the ceiling problem, but those are good questions. We should discuss that further. So we look at the ceiling problem again, right? So what would the 2 FRs be if we were just going to start fresh instead of saying, geez, what 1930s parameters can we use to try to solve this problem? And said, all right, what are we trying to do? Let's provide sealing and protect the soft counterface, right? So we get some sort of polymer that's rubbing this in, so let's make sure that it seals. And so that's an issue, right? You got a seal, you don't want scratches going by the seal. One of the funny things that happens on the shafts is it gets turned and you put a helix around it. And then, and because the shafts and the motors tend to turn in the same direction as the shafts on the lathes, you just make an Archimedes screw and you just pump the oil right out of the engine, right by the seal. And I've heard a couple times about people reinventing Archimedes screw to pump oil out of their engines. All right, so a little bit more about the structure as we get into this. So as we're trying to structure the problem, we've got the customer needs that we use to generate the FRs. Now in the FRs, we're going to have a hierarchy and a decomposition. I'll talk a little bit more about this. And then we need the corresponding DPs. And the way you do this decomposition is called a zigzagging process. So it's all functional based. I start off with a function, I come up with a DP. And so if my solution here is, and at the top level I might say my FR0 is something, provide sealing. And inherent in that is that it should last a long time. And then I decide, a shaft rubber system. And so now that is a constraint. So the rest of the FRs are going to be, to stop the oil from going by and then to keep the rubber from wearing out. And then I got to choose the DPs now to go along with those, and I can keep decomposing it because as I look at, design of, a car or something, I can go down and down and down until I get to the basic elements. So kind of one of the questions is if I'm doing surfaces, what is the basic element? Let's look at the problem of decomposition. We use decomposition in lots of things, but we don't ever teach it properly. And combinatorics is taught in math, but the applications and practical things we don't deal with. We do it all the time. If somebody gives you a big steak to eat, right, or let's see, to be neutral, we could say a big eggplant to eat, right? So what do you do? I can't shove the whole thing in my mouth at once. I have to cut it up somehow. So I need to decompose it. And after I've cut it up, I still have the whole thing, but they're all in little parts. So I'm starting off in design with this upper level concept and dividing it up. So we talk in axiomatic design, we talk about the parents and the children as we do the decomposition. And the sum of the children has to exactly equal the parent, which is obvious if I'm looking at it this way, but when I start doing my upper level functions and say, well, what are all the things I need there, somehow it gets muddled up, especially when you first start trying it. All right. So what we're really doing is articulating the detailed contents of the upper level. We need to kind of think of it that way. So what is a good decomposition? Now this collectively exhaustive, mutually exclusive actually comes from a book on business, the McKinney way, about a consulting firm, and they look at business problems. And they actually do mutually exclusive first and then collectively exhaustive. When I teach to engineers, I say, no, first we want to make sure we thought of everything. Like we're working on the space shuttle. Did we think of all the ways the crew could get killed? All right, let's make sure we got all of those there. The engineer's job is to try to think of everything that, that needs to be done. There are days I think I miss my calling. I should have been in anesthesiology. So collectively exhaustive, mutually exclusive, and then minimum number. We don't want any more than we absolutely need. So the best solution is going to be, of course, the minimum, right, if we're looking at scientific laws and stuff. But, all right, collectively exhaustive, mutually exclusive. So collectively exhaustive means when I split it up, I filled the whole circle. Mutually exclusive means no overlap. And one of the things is if I do a decomposition, I end up with a single child decomposition. I didn't decompose anything. I had a big steak on my plate. I put the knife and the fork down, went like that, and I still had a big steak and no little pieces, right? So I have not contributed to the solution of the problem. Either I forgot something or I just redefined it. Mutually exclusive. So let's make sure that they're not overlapping. So here's a system. So for engineers, get to do this when they take statics, right? We're going to break down a force system F here. So here's a force. We're going to break it down into a system Fx, Fy, Fz. These are mutually orthogonal, right? So they are collectively exhaustive. If I take the Fx, Fy, Fz components and add them together vectorially, I come up with F. And each of these components is 90 degrees away from the other two so that they are orthogonal or mutually exclusive. So it's good to have a theme for the decomposition. So how do we know we thought of everything? So, and then how do we know things are separate? So the themes help. And let me just give you a quick example, some examples. A theme can be temporal. Or we can do it in space. In other words, in time, how does this thing work? In space, how does it work? What kind of energetic components are there? So actually, when we're working on the crew survivability, what kind of energies are available to kill the crew was one decomposition. And another one was keep the crew alive on the launch pad, keep them alive on the insertion into orbit and so forth. The nice thing about having an other is that that way we know we're collectively exhaustive. So if we're designing, say, a safety system for a machine shop, I could start off saying protect people at the machine, or I could say protect them with a certain kind of energy in the machine shop. And then the next level I might switch and say, all right, now at the machine, let me look at the energy type, and then at the energy, let's take a look at the machine level. And in the end, we end up with these kinds of protective devices, no matter which one we did. So lots of times the decomposition path doesn't really matter because at the end we end up with the same thing. But it's nice to have a theme so that we can know that we're collectively exhaustive, mutually exclusive. So here's a surface making machine. This is an example. And this jig grinding, if you're not familiar with it, So if I have a hard material, I can't drill a hole and ream a hole in this. I want an abrasive element, so it goes in and makes a very precise hole. So we need high-speed rotation. We need this jigging motion up and down so that we don't wear the thing out inappropriately, and we can condition the hole inside of the hole. And so this thing's got to spin very fast. So the rotation, the jigging motion, and then positioning in X and Y are sort of what we need. You can get a more jig grinder for something over 100,000 to do this. And what Saint-Gobain wanted was, can we do it on a Haas mini mill, which is 20,000, or a mini mill, I'm sorry, is a $30,000 thing. And just put on an air spindle and attach the whole device. So there's the Haas mini mill, $30,000 machine. And so we did this just to show an example of this. So there's a bunch of things: provide the high-speed rotation, slow down motion, do that, right? And the software that we used you can get at axiomaticdesign.com. And so that is software for axiomatic design and design for Six Sigma. So I recommend that software for doing decompositions and sorting out the matrices to get them into triangular matrices. It's very useful stuff. And this, just to show you how the different layers, you got a hierarchy. Let's, provide rail, restraint, and Y, provide plate. And so this breaks the whole thing down into a hierarchical type of decomposition where you get FR-DP pairs. When we were doing the space shuttle, we had 2,000 something FR-DP pairs. So it's nice to have software where you can sort of click on this and contract it again and spread it out. Really, a computer is the only way to do this. To try to impress the client when we were working on this, and we had graduate students helping us, we took a room, it was about like this, and just papered the walls with the FR-DP decomposition so that when to impress the client. Here's the detail of the design, all structured, all organized. We can follow each track down. Anyway, so this is when you do the axiomatic design, it's nice to have these. You want to have the intent. So this is like FR 5.2. It actually captures the intent and the description of what this element here is. So every surface and every member in the design has an intent, and that's recorded, and that's important. We could build another Saturn V moon rocket. We have the plans. We know how to do it. We couldn't change it because the design intent has been lost. Right? The people who designed it are retired or passed away. And so if we don't have the design intent recorded with it, how do we get that? And typically when you review a design, now you look at the blueprint or something, and you're asking them, what's that for? What's that for? Oh, I think I'm starting to get it. What does that do over there? And lots of times this isn't recorded systematically anywhere. Anyway, so we designed and made this thing here at WPI. So this is made in our manufacturing labs. And here it is on the Haas Mini Mill at Saint-Gobain. Just one word, too. Lots of times we can do a design process where we say, well, here's the function that we want for the product. Here's the DPs that go with that function. All right, what sort of process variables do we need? Do we have a tool that does that? Let's design the tool. All right, what are the DPs for the tool? And if you can think about some of the big breakthroughs, and you can see some of these design cascades, integrated circuits, all right? So we need some sort of compact computational thing, which is actually originally was largely driven by having to get computation in space and controls in space. So compact computational elements, DPs, all right, so transistors, and let's integrate them. So we'll put a whole bunch of transistors on a little thing. PVs, well, we need to sort of mask and diffuse things. Well, we don't have any tools for that. So, all right, what are the FRs for these processes? And then let's develop the tools. So, all right, back to the shaft seals. And I think we're getting close here. So, we said, all right, we want to resist the flow and avoid wear. So those would be the FRs, right? So what are the DPs? Well, we could have some sort of sealing topography to make sure there's no channels going through. We're not pumping stuff by. And then, and then some kind of protective topography so that we avoid the wear. Now, at this level, too, in the decomposition, we go, all right, that's great. So are these things independent? When we would normally, I'd take you through, let's make a matrix. And if we don't know yet, I keep pushing the wrong button. If we don't know yet what the protective topography is, we say, well, as we develop this, as we drive this down, because it's a top-down design strategy, we will try to come up with things that keep this independent. So if I decompose avoid wear, so I could say, well, let's avoid abrasive wear and let's avoid adhesive wear. Collectively exhaustive, mutually exclusive? Well, we hope it's collectively exhaustive. They're mutually exclusive. Yeah, they're two different kinds of wear. Could be. All right, so that might not be a bad decomposition. So avoid abrasive wear. We need some plateau support so there's nothing sticking up into the ceiling stuff. And avoid adhesive wear. Well, let's get the lubrication components or lubrication pockets in it. Right. Now, there might be other ways of doing that, right? So we might say, well, let's make the shaft out of something different so there isn't any adhesive, something on this. But that's a different problem. The shaft's going to be made out of steel. All right, so now when I do this, I say, all right, so I've got promote the counterface life, all right, resist abrasive wear. So there's some contact zone features. I changed a little bit in this slide, sorry. As I said, I was sorting through a bunch of slides. And then lubricant pockets. So I get the lubricant pockets by rough grinding, and I get the features here by fine honing, which is the way we make the plateau hose surface. And I think I have a thing here. Oh, no, I didn't do that. Sorry. All right, so what you can do is you can set up one of those matrices. I forgot to copy that over. So you can see as we go from the DPs to the PVs, you can say, oh, the rough grinding is actually going to influence both of these things. So I have to start with the rough grinding and finish with the fine honing, as any idiot could figure out, right? But all right, so systematically it works too. So one of the questions is, now can I develop characterization parameters? This is James was asking. Why am I stuck with what 1930s parameter should I use? I've got a high-speed digital computer. I can make 1 million height measurements and hardly any time at all. So maybe I should do something different. All right, so here's the last bit of this. So often when we're making stuff, we've got material removal problems, surface finish, and dimensional tolerances. And it doesn't really stop there because you get the whole surface integrity thing. So it's not just the finish. I could say residual stresses, microstructure, composition. So there's a lot more that you could put in this. But so in machining, we're grateful to Kennametal for their support. We have to remove material and create the surface. So this violates Axiom 1 and the material remover and whole dimensional tolerances, right? So, and in some ways you could say, all right, we're just doing machining. How can we, get a solution and maybe it looks like we've got 1 DP for 2 FRs. Could we just get material removal and surface finish decoupled? And Kennametal had a while ago wiper tools. I don't know, is anybody familiar with these? All right, well what it does is, so when you're turning, the tip of the tool imprints itself here. This is not a very good drawing, right? But that's the idea. And this is this triple thing here. I get material removal, rate. So I'm designing the process. I want to get the material removed. Power, I need this is a limitation. I've got the force is going to deflect everything. So this is going to influence the dimensional tolerances. So actually, when I go to turn something on a lathe, if I just have this end hanging out, as I often do, and I just run the tool down here, it's a cantilever beam, and the end deflects more than here, because here's where I've got it chucked up. And so this ends up being fatter than this because it deflects more when the tool hits, so the force is important. Anyway, so here's the way the roughness sort of comes together. There's a little development you can do, but basically the roughness, peak to valley roughness, because that's the easy one to do, right, is the feed square divided by 8 times the nose radius. Well, the feed is one of the big deals in how fast do I get the material off, because this tells me how far do I move the tool along every time the piece revolves around. And so this is making this helical groove down the piece that I can use to pump oil by the seal if I'm not careful. And so this is what it looks like. So here's the helical groove. The light things are the high regions, the dark things are the bottoms. And so there's a piece of turned surface measured with an interferometric microscope. So I want to control the surface finish, control the material removal rate, control the shape. So if I'm in manufacturing, it'd be nice to control these, so when somebody comes in and says, I need this, this, and this, I know how to do it. So what are my DPs? So I'll feed, speed, depth of cut, tool. I got 4 DPs, 3 FRs. I got too many, so I need to decide which ones I'm going to use. What kind of constraints do I have? Well, power, force, because I might break things if I go to too high a force. And usually they tell me you're going to make it out of this stuff, and you don't have any choice. So I could set up my matrix. So FRs 1, 2, and 3. There's the DPs, or this is. So I could call these FRs, or I could call these now. These are actually DPs for the part, and these are the process variables here. So same sort of matrix problem. And here's the functionality. So I look at this functionality. The finish is a function of the feed and the tool. So I've got to put X's here. So the tool influences the finish, and the feed influences the finish. So I get X and X there. To a first approximation, the speed does not influence the finish, and neither does the depth of cut. We could get fussier about that. Material removal rate, feed, depth of cut, and speed all influence the material removal rate. And then the shape is basically the force, and the force is the function of the tool, feed, and depth of cut. So we've got a messy looking matrix here. And clearly I would have to iterate to get the right solution. And typically that's what happens when you set up a machining process. The engineer sort of abdicates their role and throws this at somebody from the tech school and says, here, get this set up so this works right. That's why you did your tech school stuff. And now I'm going to go have a cup of coffee and draw pictures on papers, because that's what engineers do. And you actually have to make the stuff. So work it out. So anyway, so one of the things you do is you eliminate one of the process variables that you're not going to use, and this, you can actually, in this case, it doesn't matter which one you choose. Sometimes there's an easier one, but so we'll select 3 what I'm calling DPs, but they could be process variables as well. And we still have these messy looking matrices, right? So the way we know it's messy looking is we get the diagonal, and then we've got an X up there and an X down there. And so there's no clear order of adjustment. If I had a nice triangular matrix, I know I would just go boom, 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 and there wouldn't be any iteration. But here I I select the tool, and that does something to the finish and the shape. I select the speed, that does something to the material removal rate. Then I select the depth of cut, boom, boom, and that changes the shape tolerance. Now I've got to go back and maybe change the tool to change the shape tolerance. So you see that I get into an iteration. So solution 1, all right, so let's take this, and then can I sort out that matrix? And the way you do this, the software, the Eclairo software does this for you. But, and in the full class I do this, it's sort of like a game. I can take the rows and switch them, and then I can take the columns and switch them. So the DPs come along with a column, and the FRs go along with the rows, and with the right sort of switching and exchanging around, sort of like a little game, kind of like a Rubik's Cube kind of thing, right? Except easier. Because I can't do the Rubik's Cube, and I can manage this. I can rearrange this. So now I'll select the tool for the surface finish. It's going to do something to the shape tolerance that I might not like. Then I'll select the depth of cut. That's not going to do anything to the finish, and I'll get the depth of cut, so the shape tolerance is good. That's going to influence the material removal rate, so then I'll do the speed, so I get the material removal rate, then I can sort of balance my transfer line in the factory and move the parts along at the right speed with all the right things. Solution 2, in this case, somebody said, you're going to use the tool from the tool crib, work it out. All right, so now I've got these 3 things, and similarly, I can figure this one out. I get the feed to get the finish, but that's going to change the shape tolerance and the material removal rate. Then I get the depth of cut to get the shape tolerance. That's going to change the material removal rate again, but then I adjust the speed, so I make the parts in step with everything else. So there's the turned surface finish, and Well, we'll save that for coffee break. Let's see, I think road design, okay. So here's the question. And actually when I got all through doing this morning. I got up at 4 something and got in here to finish working on this. I got all through doing it. I looked at the title and it said, uh-oh, because Hassan said he was going to do multi-scale. I had multi-scale in the title. Uh-oh, where's that? I go, oh yeah, here it is. So if you've been looking for a lot of multi-scale, come to the next two because there's more multi-scale. Those are all about multi-scale. But the scale is a direction in which you can do decomposition that we often ignore. So we say, what's going on at different scales? Well, we ignore it. We've got form, waviness, and roughness. So then but can we break it down even further and get more detail? But here's a simple breakdown for this. Let's take a look at a road. We would like a smooth ride and adequate friction. The DPs are a smooth surface and a rough surface, and we've got a bunch of things like this, oil lubricated bearings, right? So we need roughness to retain the oil, but we don't want to scar the counterface. So we've got, and just like in the seals, so we've got several things that need to be done. In this case, we can do it at different scales. So I'm going to be showing in the next two things, and I showed yesterday, this area scale plot. So the way this works basically is at large scales, the relative area seems to be 1, and then I get into finer scales and I start seeing these ups and downs, and this is all this fractal, chaotic nature of the surface, and the area seems to go up and up. When the relative area is 1, that means if I put something on the surface, it stays flat. I was working with a tire company on this, and we did an analysis for them, and I said, well, the way this works out, looking at the analysis, if I took a nickel and put it on your tire, anywhere I wanted to, it would sit flat. And the guy goes, we call this a nickel tire just for that reason. and so that, but if I take a dime, it's going to tilt in. Yes. And so that's above the smooth rough crossover. So at large scales, things are smooth. The rug is smooth at the scale of my foot. I walk on it without any trouble. But if I'm worried about dust, it's rough. Anyway, so for the wheel-road interaction, I want a smooth surface. So I want to avoid holes that are large on the scale of the diameter of the tire, right? Because that would make for a very rough ride. Now, on the the tread and the compound's important in here too, not just the tread, that interaction, I want a surface that is rough, and the guys that make the road surfaces call this texture and microtexture, and this is roughness up here. That's just their civil engineer's name for the stuff. But if I have this right kind of characterization, I can say, I can decouple these two functions on one surface, and I can make a surface that looks smooth to the wheel and rough to the tire by doing a decomposition in scale. And so I can keep these two things independent because the interactions that control them are happening at two different scales. And so if we look at the surfaces that we're designing, we can see there's a bunch of surfaces like that. We've got so light interaction at one scale and something else at another scale. Anyway, so we're grateful for support from lots of different sources. And this SFRAC software does the area scale analysis. Yeah, I'm grateful for my own support. This is more like an acknowledgement that if I seem enthusiastic about this, it's because it's mine. So it's just being honest about it. All right. So thank you for your attention. It wasn't too bad. I went over by 6 minutes of 2 course worth of material. So, and a number of you got a few questions right at the end of the first half. So.
How are your next 3 different? Your next 3 lectures?
I hope there's only 2 more.
Part 1, part 2. Oh, you're right. Oh, you're next.